In today's video, we're going to examine the reactivity series of metals and observe how different metals react when combined with both acids and water. Then, to conclude, we will take a quick look at how the reactivity series can help us determine the outcomes of displacement reactions. The reactivity series is based on the behavior of metals and their tendency to lose electrons. All metals share a common feature in their atomic structure. They contain electrons in their outermost shell that they are eager to shed. When metals react with other substances, they release these outer shell electrons and, in doing so, form positively charged ions. Therefore, when we refer to a metal's reactivity, we're simply talking about how easily it forms positive ions. The more easily a metal gives up its electrons and forms ions, the more reactive it is considered to be. By observing and comparing the reactivity of various metals, we can place them in a specific order based on how reactive they are, and this arrangement is what we call the reactivity series. Although carbon and hydrogen are not metals, they are often included in the series as reference points to allow for better comparison of metal reactivities. At the top of the reactivity series, we find the group 1 metals, which are the most reactive. These are followed by the group 2 metals, which are slightly less reactive. At the bottom, we have the transition metals, which are generally the least reactive. In order to establish the reactivity series in the first place, scientists react each metal with either an acid or water, and then compare how fast or how violently each reaction occurs. When a metal reacts with an acid, the result is the formation of a salt and hydrogen gas. For example, if we were to react potassium with hydrochloric acid, we would produce potassium chloride and hydrogen gas. Due to the extreme reactivity of potassium, this reaction would be very explosive, possibly producing fire or sparks and generating large volumes of hydrogen gas. As we move down the reactivity series, these reactions become gradually less intense. By the time we get to magnesium, the reaction would be much calmer, with the metals simply bubbling and disappearing in the acid. Further down the series, we would observe even fewer bubbles when reacting zinc or iron, and by the time we get to copper, it usually would not react at all with the acid. Rather than relying solely on visual observation of how violent each reaction is, we can also measure the temperature change during each reaction. The more reactive the metal, the more heat it produces during the reaction. However, to ensure that we are conducting a fair comparison, we must control the experiment. This means using equal masses and equal surface areas of each metal sample, as well as the same type and concentration of acid for every reaction. Now, if instead of acids, we react metals with water, the products formed are metal hydroxides and hydrogen gas. For instance, lithium reacting with water would produce lithium hydroxide and hydrogen gas. However, only the most reactive metals can actually do this. Metals like zinc, iron, and copper will not react with water at all, while magnesium will react only slightly. Finally, let us discuss displacement reactions, which are based on the principle that a more reactive metal can displace a less reactive metal from a compound. For example, if we place a strip of magnesium into a solution of iron sulfate, the magnesium will displace the iron, forming magnesium sulfate and releasing elemental iron. This occurs because magnesium is more reactive than iron. However, if we try to do the same with copper, placing it into a solution of iron sulfate, no reaction will take place. This is because copper is less reactive than iron and therefore cannot displace it from its compound. That concludes our video for today. If you found this lesson helpful, please remember to give it a like and share it with your friends. We look forward to seeing you in the next video.